Thanks for coming back. Today we're going to continue in our unit and talk about similarity with transformations. So we've been working with similarity and similar figures. We studied transformations. Now we're going to put them together. Get your notes page ready, whether you're taking notes on your own paper, you printed mine, or you're using the Google Slide. Here we go. The learning target for today is I can use transformations to create similar figures. And again, we know transformations, there's 4 kinds: translations, reflections, rotations, and dilations. And similar figures are figures with the same shape but different size. All right, so how do I determine if 2 figures are similar because transformations were used is basically what we're looking at today. So first example, I have 2 right triangles on a coordinate grid, triangle UST and triangle RPQ. So the first thing you're going to ask yourself is just like you're kind of predicting using your math skills, what you know about transformations. What transformations does it look like happened to triangle SUT? So we started with the blue, we went to the green. I can see 2 things happening here. The direction of the triangle changes, and what would cause that would be a reflection, if we could say that the y-axis was here. So a reflection over the y-axis. And then the size definitely changed. So which transformation deals with that? That would be a dilation. So this is what looks like happened: a reflection over the y-axis and a dilation, okay? Now we need to prove that those things did happen. So as far as the reflection goes, that could have occurred. You know, your y-axis is here, and you can reflect that over. U becomes R, T becomes Q, and S becomes P, but after another transformation, of course. So a reflection could occur, okay? Now, as far as the dilation goes, we're going to prove that mathematically by using what we've been practicing in the last couple lessons. So this is a proof right here for dilation. Let's write what we know about the sides of triangle SUT. We'll call it the small triangle, the blue triangle, whatever you want to call it, triangle SUT. ST is 3 units. I'm getting this by counting from S to T, 1, 2, 3. So ST is 3, TU is 5, SU is our hypotenuse. We can't count that, but what can we use to find that? The Pythagorean theorem. Yep, so you could do a squared plus b squared equals c squared, 3 squared plus 5 squared equals c squared, and go on from there, okay? The big triangle, or the green triangle, PQ, which is the vertical leg, 1, 2, 3, 4, 5, is 6 units. QR, the horizontal leg, is 10 units. And again, we don't know that hypotenuse, but we could use the Pythagorean theorem to find it. So now let's set up our ratios, okay? PQ corresponds to ST. They're both the vertical leg. PQ is 6, ST is 3. 6 over 3 simplifies to 2 over 1. So the ratio is 2 over 1. For the horizontal legs, QR corresponds to TU. 10 over 5 also simplifies to 2 over 1. The ratio is the same. And what we said about that is when you have the same ratio, the same scale, the same K, you have similar triangles. So then you would say triangle SUT is similar to triangle PRQ because corresponding side ratios are congruent. Use your math vocabulary. A reflection and a dilation were used to enlarge and move triangle SUT. And the scale, the K, is 2. Write down everything you know. Show off your math, okay? We've been practicing these transformations. We've been practicing ratios and scale. Our vocabulary, put it all together. Use it. Make a nice little statement there for your proof. All right, let's look at another example. Remember, you can pause these at any time. All right, so again, maybe I shouldn't move that up. Yep. What does it look like happened to right trapezoid ABCD? I know it's a right trapezoid, it's got two right angles. Well, what transformations could have happened here? Well, EFGH looks smaller, and when you change the size, that's dilation. And it also moved on the coordinate plane. It didn't change positions. AB hasn't reversed to become EF. So when it moves on the coordinate plane, which one is that? Translation. And you can see it in your notes. So a translation up and to the right with a dilation occurring is our guess. Now we need to prove it. The translation, yeah, that could have occurred up and to the right. Okay, we see that that could have happened. What we need to really prove is, did the dilation occur? Was there a decrease in the size? So here's our proof. We're going to again count to get side length. So we're going to start with the big right trapezoid, side length AB, 1, 2, 3 from A to B. AD or DA, 1, 2, 3, 4, 5. And we can do DC too, or CD, 1, 2, 3, 4, 5. Okay. The only one we can't get is the slant. We can't get that horizontal, the slanted side, not horizontal. Okay, so that's on the blue one. Now let's go to the small one, the green one. EF would correspond to AB, so I'm going to start with EF as 2. Then EH would correspond to DA, 1, 2, 3, 4. Here it is, HE. And GH, 1, 2, 3, 4, is also 4. Okay, so I've got my corresponding sides lined up here, but I'm going to write my ratios. AB corresponds to EF. AB is 3, EF is 2. So 3 over 2. Okay. DA and HE, 5 over 4. Not the same ratio. And our last one, CD to GH, is also 5 over 4, but it doesn't all three match. So because that doesn't happen, I don't think I said that was correct, but because they're not all congruent, they are not similar right trapezoids, because not all the corresponding side ratios are congruent. So in order to be similar with transformations occurring, especially the dilation, you have to have those corresponding side ratios congruent all the way across. Okay, if you have any questions, write them down, write them on your notes. If I'm asking you to submit these notes, I will look those over when you submit them, and we will do some practice. Thanks for tuning in.